Welcome to the lecture on flexible AC transmission system. This lecture will be the continuation of our previous lecture on TS-TCR type of SVC. In this lecture, we will see the operating VI characteristics of the TS-TCR type of the SVC. That is with the two TSC branches. So, here we can see that this is the admittance curve. We know the rating of the TSC is little below than the TCR rating. So we are getting here VC max is slightly less than this real max. Now we can see that here is the current IC, that is capacitive current, on the left side of the x-axis, and IF, that is inductive current, will be on the right side of this x-axis, and voltage feedback towards the y-axis of it. So you can choose here the compensation level for the fuel depending on the amount of current you are passing through, and that will depend on the voltage rating of the supply. So for the TSC1 we will get the curve of BC or line of BC till this point, and when two TSC branches are switched on, we will get the 2 times of the BC, that is 2 BC. So we are seeing here for only 2 TSCs, so our BC max will be equal to 2 times of BC, and our BL max, we are having only one TCR branch, so we will get the characteristics of this only one TCR branch, and our BL will be equal to PL max for this TCR branch, and this will be the IL max, that is the inductive current of the TCR. Now we will see that VC max is the voltage limit for the TSC. So this VC max is slightly below than the VL max, because VL max we have to keep somehow larger than the VC max to avoid the short circuit or circulating current. Now VL max is the voltage limit of this TCR. IC max is the capacitive current limit. So IC max may be equal to 2 IC or it may be 3 IC depending on the number of TSC units. So for 2 TSC units, IC max will be equal to 2 IC. BL max is the maximum admittance of the TCR, and that is fixed because for TCR branch will be only one. BC is the admittance of the TSC. So this BC, for one TSC branch there will be 2 BC, for the 2 TSC branch there will be 3 BC for 3 TSC branch, and so on. So we will get, depending on the number of TSC branch, we will get the BC max as equal to N, that is number of units multiplied by BC, that is admittance of one TSC branch. Now we will see the advantages of the TSC-TCR type of SVC. So here you have a fully controlled capacitor in the TSC-TCR type of the SVC, unlike in the FC-TCR type of SVC or MSC-TCR type of SVC, where in FC-TCR type of SVC we were having with a fixed capacitor, and in MSC-TCR type of SVC we were having of the mechanically switched capacitor. So there was a limited control of the capacitor, but here we are having the fully controlled capacitor. So because of this advantage, we are getting the reduction of the reactor size, because you can have a step or size of TSC. So the reactor size will be the one step size of the one TSC. So instead of keeping the reactor size equal to the total maximum capacity of the TSC, we are having the reactor size equal to only one step size of the TSC. So stepwise here we can control, and our reactor size is reducing here. So consequently the harmonics is also generated, but that harmonics will be less here, and that for that we will require to separate the harmonics, and we have to use the harmonic filters. So moving towards the second advantage, that is this type of TSC TCR type of SVC got the greater flexibility of the control, and precision can be set by the TCR. So here we are getting the greater flexibility to control this TSC TCR because of the stepwise control of each TSC branch, and we can set the precise value or smooth control we can provide with the help of this TCR. So moving towards the next advantage, this TSC TCR type of the SVC has the better performance under the fault conditions, because you have switches for the TSC, and you can switch on and switch off the TSC branches as per our need, and you can switch it in the impedance part of the fault. That is our great advantage. So our impedance falls or impedance rises. So in case of fault, our impedance falls below certain limit, so we can switch the impedance of the fault, and we can dampen the oscillations which are present in the systems by switching this impedance. And the last advantage is it has the power losses in the quiescent or idle operating conditions. That is, when the SVC output current is close to equal to 0, the power losses tends to be less with this TSC TCR type of the SVC than the normal one. So when our TSC branches are in the idle conditions, they does not consume any current or any power, and consequently our loss will be minimized. So in this type of TCR type of SVC, we will get the very low power loss, and there is a no power loss or very low power loss in the ideal operating conditions. Thank you.